Section 7.3, Radiation. So we know that heat can be transferred by means of conduction from two things being physically in contact with one another. We know that it can be transferred by convection, by fluids moving, but we also know that the Earth is heated by the sun. So how is that heat transferred? And that heat is transferred by means of electromagnetic waves or radiation. So any object that's at any temperature emits radiant energy over some range of frequencies. The peak frequency at which that object radiates is entirely related to the temperature of the object. The hotter it gets, the higher that frequency goes. So for example, if you turn the burner up on your stove, then after a little while it'll get really, really hot. At about 500 degrees Celsius, it will emit visible light. It'll look red. If you turn the lights off, it would glow. You could see it in the room. If it were to continue to heat up and heat up and heat up, it will start to emit multiple visible wavelengths, and it'll appear white. The sun is really, really hot, and so it emits energy in that white hot, very hot range where we can see it. So the peak frequency of the sun's radiation is in the visible range for humans. Now compared to the sun, the Earth is not nearly as hot, but it does still emit radiation, known as terrestrial radiation. That radiation is emitted in the form of electromagnetic waves known as infrared waves. Infrared waves are what everyday objects give off. For example, if you walk up next to a person and put your hand close to them, you can feel the heat from that person. That is because that person is at a particular temperature, and they emit infrared waves. You can't see it because it's not hot enough to emit light that your eyes can pick up, but you can feel it if you get close to someone. Infrared waves are sometimes known as heat radiation, and you can feel this even if you just stand next to an open stove. So you might wonder, if everything's emitting energy and energy is conserved, how is it that objects don't just use up all the energy that they have? And that's because they also absorb energy as they emit energy. So all of the sunlight that hits you, all of the energy from the air in the room, you absorb that as you go about your daily life and re-emit it as heat energy, as infrared waves. Most objects that are good emitters of energy are also good absorbers of energy. So they can absorb a lot of energy, but they can also emit a lot of it right back out. So the temperature doesn't really change too much. Good emitters don't run out of energy because they absorb so much energy as they give it off. But you also see that the temperature of those substances doesn't go up. Objects that are poor emitters tend to be poor absorbers. So if the object only gives off a little bit of energy, it tends to only absorb a little bit of energy. The surface of any material both absorbs and emits radiant energy. If a surface absorbs more energy than it emits, then we call it a net absorber, and that object will see that its temperature increases. It's absorbing energy and not giving as much off, and so the molecules are moving faster, so the temperature goes up. If it emits more than it absorbs, then we call it a net emitter, and the temperature will fall, giving away more energy, and the object will cool off. Whether or not something is a net absorber or a net emitter is determined by what it's around. If the object is hotter than its surroundings, then it's going to cool. If the object is cooler than its surroundings, it's going to warm. The hotter object emits energy and it cools off. The cooler object absorbs energy and it warms up. And that process continues until you reach thermal equilibrium, until everything is moving at the same speed and they all have the same temperature. So it may seem that absorption and emission are opposite processes, but they're not. They're actually separate processes. Because remember, whether it emits or absorbs depends on its surrounding. The opposite process of absorption is reflection. And this occurs when some type of energy, particularly some type of radiant energy, hits a boundary or a surface. Some of that radiant energy will be absorbed and some of it will be reflected. Those are opposite processes that occur at one instant. If you have something that's a good absorber, it reflects very little light. The surface will appear dark. So this is why when you wear dark colored clothes in the summer, you feel hotter. This is why people with darker cars in the summer, the cars themselves will be hotter. This is why asphalt in the summer is hotter than concrete. Darker surfaces absorb more energy and they warm up and they get hotter. Another interesting thing that occurs here is if you have a small opening in a doorway, and I mean, you can test and see how small it would be depending on where you observe it from, but from any distance, a really small opening in a doorway is always going to appear dark, even if there's light in the other room. And that's because when the light reaches that boundary, it bounces off a whole bunch of times and never quite makes it through. And so it appears dark. Because of all the reflecting on that boundary, the light energy gets absorbed. Less light energy means the opening appears dark. Conversely, good reflectors are poor absorbers. So lighter colors do not absorb as much heat energy as darker colors. Clean snow is a very good reflector of energy, and so it'll reflect away a lot of sunlight and will not melt as fast. Dirtier snow will melt much quicker. The dirt and things inside the snow will absorb more of the energy. The snow will melt away much faster.